Welcome to your personalized deep dive. Today, we're taking you right to the edge of a black hole.
To the edge.
Yeah, to explore this fascinating world of black hole magnetospheres.
Exactly. We're basing our deep dive on this research paper.
Okay.
It has a pretty complex title, but we'll break it down for you.
Yeah.
It's called Vacuum Magnetospheres Around Kerr Black Holes with a Thin Disk.
All right, so we'll unpack all that. We'll unpack how these invisible giants generate electric fields and how some act like magnets, thanks to something called the black hole Meissner effect.
Right.
And what all this means for cutting-edge astrophysics research.
Yeah, it's going to be good.
Yeah.
Think of it as your shortcut to understanding some of the most powerful forces in the universe.
Okay, let's unpack this.
Yeah.
First things first, what is a black hole magnetosphere?
So imagine a region around a black hole where magnetic fields dominate,
Okay.
even stronger than the surrounding plasma.
Wow.
That's the magnetosphere. And these things are key players in some of the most energetic events in the universe.
Wow.
So we're talking active galactic nuclei,
Yeah.
compact X-ray sources, even gamma-ray bursts.
Okay, so these are huge.
Huge.
Yeah.
Yeah.
So this research paper, what's the big question these researchers are trying to answer?
Well, they're focusing on a simplified model of a black hole magnetosphere.
Okay.
It's called a vacuum model.
A vacuum.
Yeah.
But aren't black holes surrounded by all kinds of stuff?
They are.
Like gas and dust and radiation?
Absolutely.
Yeah.
But by assuming a vacuum,
Okay.
researchers can isolate the interaction between gravity and electromagnetism
Okay.
without all that extra stuff.
Got it.
It helps them focus on how the black hole's spin shapes the surrounding electromagnetic field.
So it's like a controlled experiment,
Yeah.
strip things down to see the core forces at work.
That's a great way to put it.
Okay, you mentioned the black hole spin.
Right.
This paper looks at Kerr black holes.
Mm-hmm.
What are those?
A Kerr black hole is simply a rotating black hole.
Okay.
And it's this rotation
Okay.
that creates electric fields within the magnetosphere.
Wow.
It's almost like the black hole itself is a giant electric generator.
A giant electric generator.
Yeah.
Okay, we've got a spinning black hole,
Mm-hmm.
a strong magnetic field,
Yes.
and now an electric field too.
That's right.
What about this thin disk
Yes.
the researchers are modeling?
Yeah.
Where does that fit in?
So picture a flat disk of material
Okay.
carrying an electric current,
Okay.
situated around the black hole's equator.
Okay.
It's like a ring of electricity circling the black hole's waistline.
A cosmic hula hoop.
I like that.
Okay.
That's a good one.
But why is this disk important?
This disk is the source of the magnetic field.
Okay.
It's the electric current within the disk that generates those magnetic field lines,
Okay.
extending out into the magnetosphere.
So the disk is like the magnetic seed,
Mm-hmm.
and the black hole's rotation shapes those field lines.
Exactly.
I like it.
Yeah.
Okay.
But there's a twist.
Oh.
Their model gives this disk an inner edge,
Okay.
meaning there's no current flowing between the disk and the black hole's event horizon,
Okay.
the point of no return.
Interesting. So no current near the event horizon.
Mm-hmm.
What about that current reversal you
Yeah.
mentioned earlier?
Here's where things get really interesting.
Okay.
In their model, the current flowing within the disk actually reverses direction at a specific point.
Really?
Yeah.
At a certain point.
At a certain point,
Just reverses.
it reverses.
Right.
Imagine it flowing clockwise up to a certain point and then suddenly switching to counterclockwise.
Okay, so a sort of magnetic flip-flop happening within the disk.
Yeah, I like that analogy.
Okay, what does that do to the magnetosphere?
It creates a dividing line.
Well,
They call it the separatrix curve,
Okay.
separating the magnetosphere into two distinct zones,
Okay.
inner and outer.
A magnetic border.
Yeah.
Okay. I'm intrigued. What's happening in these two regions?
In the inner region, some magnetic field lines loop around the inner edge of the disk,
Okay.
while others connect the disk directly to the black hole's event horizon.
So some magnetic lines are looping around and others are diving right into the black hole.
That's right.
What about the outer region?
In the outer region, the magnetic field lines stretch out from the disk,
Okay.
like a vast cosmic spiderweb connecting to distant regions of space.
Okay, so two distinct magnetic zones around a single black hole.
Mm-hmm.
That's wild.
Yeah.
Now, what about this black hole Meissner effect?
Right.
What did the researchers discover?
This is where things get really mind-bending.
Okay.
The black hole Meissner effect occurs in rapidly rotating black holes. Essentially, it's like the black hole is repelling the magnetic field, preventing it from entering the event horizon.
It's like the black hole is a giant no trespassing sign for a magnetic field.
Exactly.
Yeah.
And it's similar to a phenomenon seen in superconductors called the Meissner effect.
So in a way, these black holes are acting like massive cosmic superconductors.
That's a good analogy.
Okay, my mind is officially blown.
I told you it was mind-bending.
Yeah.
Yeah.
We talked a lot about the magnetic field. But what about the electric field?
Right.
How does it fit in?
Remember how we talked about the black hole's rotation being key?
Yes.
Well, that rotation generates the electric field.
Okay.
The faster the black hole spins,
Okay.
the stronger the electric field.
So it's like the black hole spin is cranking up the voltage.
Exactly.
Okay.
And for black holes spinning at the theoretical limit,
Okay.
the event horizon becomes what we call an equipotential surface.
Equipotential surface. Break that down for me.
Okay, so imagine it like this on an equipotential surface.
Okay.
There's no difference in electrical potential between any 2 points.
Okay.
So even though there's a strong electric field overall, the event horizon itself is like an electrically neutral zone.
Interesting. What else did they find out about the electric field?
They discovered a saddle point in the electric potential right on the black hole's axis of rotation within that separatrix curve we discussed earlier.
Okay, saddle point, help me visualize that.
So think of a mountain pass.
Okay.
That's what the saddle point is like for the electric field.
Got it.
It changes direction at this point, kind of like a fork in the road for charged particles.
That makes sense. Now, how do these magnetic and electric fields affect charged particles in the magnetosphere?
Yeah.
Specifically, what about particle acceleration and accretion?
Well, this is where things get really exciting.
Okay.
Because we're talking about the kinds of processes that could power those incredible jets of energy we see shooting out from active galaxies.
Okay, so how does particle acceleration work in this scenario?
Imagine charged particles, like protons or electrons, getting caught in the magnetic field lines.
Okay.
These lines act like guides, creating a kind of cosmic racetrack.
So they're trapped on these magnetic tracks, spiraling along. What happens then?
As they spiral, the electric field, running parallel to the magnetic field lines, propels them forward, accelerating them to incredible speeds.
Wow.
Some even approach the speed of light.
Wow, like a cosmic particle accelerator?
Exactly.
What happens to those super fast particles?
Some might collide with other particles, releasing their energy as high-energy radiation like gamma rays, which could explain some of those intense gamma ray bursts we've observed.
That's fascinating. What about the other particles?
Some may escape the magnetosphere entirely, forming the jets of matter and energy we see in active galaxies.
Those jets are enormous, spanning thousands of light years.
Right.
To think they might be fueled by these tiny particles accelerated around a black hole.
Yeah, it's mind-blowing.
It's incredible, right?
Yeah.
Now let's talk about accretion.
Okay.
The process of matter falling onto the black hole. Remember those magnetic field lines connecting the disk to the event horizon?
Yes.
And I remember you said the electric field might be pulling positively charged particles down those lines.
That's right.
Towards the black hole.
Exactly. The electric field creates a potential difference along those field lines. And those positively charged particles are drawn down towards the black hole.
Okay.
Like they're sliding down a cosmic water slide.
So the electric field is like a cosmic vacuum cleaner.
Yeah.
Sucking particles into the black hole.
Yeah, I like that.
What happens to those particles?
Well, they can contribute to the growth of the black hole's mass.
Okay.
But here's the really interesting part.
Okay.
Because they're positively charged.
Yeah.
They could also cause the black hole to gradually accumulate a positive charge over time.
So the black hole isn't just gobbling up matter. It's acting like a giant battery building up an electric charge.
It is. That's a great way to put it.
While the amount of charge a black hole might gain is still being researched, it could be significant enough to change the magnetosphere's entire structure.
Absolutely, especially for supermassive black holes.
So it's a constantly changing system.
Yes.
Where the black hole's growing charge feeds back into the magnetosphere, changing the fields and how particles move within them.
Exactly.
This is a lot to wrap my head around.
It is a lot, but you're doing great.
Thanks.
We've covered a lot of ground in this first part of our deep dive.
Yeah.
We've explored the structure of black hole magnetospheres, those looping magnetic field lines, the electric fields that act like particle accelerators, and even touched on the idea of black holes accumulating electric charge.
It's incredible to think about all these complex processes happening billions of light years away.
Right.
And we're here trying to unravel these mysteries.
Yeah.
What are some key takeaways you want our listener to remember from our discussion so far?
So here's what stands out to me.
Okay.
Black hole magnetospheres aren't just theoretical ideas. They're dynamic systems that power some of the most energetic events in the universe.
Wow.
The black hole's spin is crucial in generating the electric field and shaping the entire magnetosphere.
Okay.
And finally, this research, while focusing on a simplified vacuum model, gives us incredible insights into the forces at play around black holes.
Great points. And for you listening, the big takeaway is that black hole magnetospheres are much more than just interesting structures.
Right.
They're powerful engines driving some of those incredible events in the universe.
Exactly. Now, in the next part of our deep dive, we'll explore some of the specific research methods used to reach these conclusions.
Okay.
And delve a little deeper into the black hole Meissner effect.
Sounds good.
Stay tuned.
All right. Okay.
See you soon.
Take care.
Welcome back to our deep dive into black hole magnetospheres.
Yeah.
Before we jumped into all the exciting implications, we were talking about this thin disk model the researchers use.
Right.
It seemed pretty key to their findings.
It really was.
Yeah. This disk model, with its electric current and that intriguing current reversal, really helped them unlock a lot of insights into the structure and behavior of the magnetosphere.
Right. So how did they actually go about studying this model?
Yeah.
Did they build a mini black hole in a lab or something?
Not quite. They used sophisticated mathematical tools to model the complex physics happening around a black hole.
Okay, walk me through it.
Okay.
What kind of tools are we talking about?
Well, they used a combination of approaches.
Okay.
One important tool was a mathematical framework called the Newman-Penrose formalism.
Newman-Penrose formalism.
Yeah.
That sounds a bit intimidating.
It's a mouthful.
Yeah.
Can you break that down for me? Think of it like a specialized physics calculator. Designed specifically for dealing with the warped space and time around a black hole.
Got it. A black hole calculator.
Basically.
So they use this to figure out how electric and magnetic fields behave near a spinning black hole.
Exactly. They tackled this by first focusing on the vacuum regions. Above and below the disk, where there's no matter present.
So they broke the problem into smaller, more manageable chunks.
Yeah.
Solve the equations for the empty space first.
Right.
And then figure out how to connect those solutions to the disk itself.
Precisely. And to connect everything smoothly at the disk, they use something called junction conditions.
Junction conditions. What are those exactly?
Essentially, they're like a set of rules that tell us how the electric and magnetic fields have to behave as you cross the disk. It's like making sure the puzzle pieces fit together seamlessly.
So they're using these junction conditions to make sure the solutions for the regions above and below the disk match up perfectly at the disk itself.
Right. Now, to make their model more manageable, they made a couple of simplifying assumptions.
What kind of assumptions?
First, they assumed that the black hole itself had no net electric or magnetic charge. It's like starting with a clean slate before adding in the effects of the disk.
That makes sense. Keep things simple to start.
Right.
What was the other assumption?
They also assumed there was no electric charge on the disk itself. At least initially. Remember, the disk carries an electric current, but that doesn't necessarily mean it has an overall charge.
Right, like a wire carrying electricity doesn't necessarily have a net charge itself.
Exactly. So they started with a neutral disk and a neutral black hole, focusing solely on the effects of the black hole's spin and that electric current flowing in the disk.
Got it. So they're honing in on the most important drivers of the magnetosphere. Now, how did they actually model that electric current?
Right.
We talked about it reversing direction. But how did they describe that mathematically?
They used a model where the current density or the amount of current flowing through a given area decreases as you move further away from the black hole.
That seems logical. the current would be strongest near the black hole, where its gravitational pull is most intense.
Exactly. And to achieve that current reversal, they used a specific mathematical technique involving what are called Legendre functions.
Legendre functions.
Oh, okay. So I'll trust you on the math.
Well, don't worry about the details.
Yeah.
The important thing is they found a way to mathematically describe that current flip-flopping within the disk.
Okay, so what happens next? How do they use this model to figure out the magnetic field?
Once they had a good mathematical description of the current, they applied Maxwell's equations, those fundamental laws of electromagnetism, to determine the magnetic field lines throughout the magnetosphere.
Okay, so they use those equations to essentially map out the magnetic field based on the current flowing in the disks.
Exactly.
And that's how they found that separation between the inner and outer regions of the magnetosphere.
Precisely. They discovered that the current reversal in the disk creates that dividing line, the separatrix curve, which separates the looping field lines closer to the black hole from those extending outward in the outer region.
It's incredible how this model, even though it's simplified, can reveal such complex structures.
I know. It's pretty amazing.
Yeah, within the magnetosphere.
It is remarkable. And remember, we're still talking about the vacuum scenario.
Right.
In reality, there's likely matter present, which adds another layer of complexity.
Right. We're focusing on the fundamental forces before adding in all the extra bells and whistles.
Exactly.
But even with this simplified model, we're seeing some incredible physics at play.
Absolutely. Now, let's shift our focus to the electric field for a moment. Remember, even though we started with no net charge on the disk, the black hole's rotation induces an electric field.
It's like the black hole itself is generating an electric field. Just by spinning. And the faster it spins, the stronger the field. Precisely. And remember that saddle point we discussed earlier? That point where the electric potential changes direction?
Yes, like the mountain pass. Well, that saddle point turns out to be incredibly important in understanding how charged particles move within the magnetosphere. It's like a fork in the road, guiding particles along different paths, depending on their charge and energy. So the electric field, in combination with that complex magnetic field structure, creates a sort of intricate dance for charged particles. This is all starting to come together now.
Good.
We've got a model with a spinning black hole, a thin disk with reversing current, and the resulting magnetic and electric fields guiding the movement of charged particles.
Exactly. And in the final part of our deep dive, we'll explore the fascinating implications of this model, including how it could explain the powerful jets we see shooting out from active galaxies.
I can't wait to hear more. Welcome back to the deep dive. We spent the last two parts building up this incredible model of a black hole magnetosphere. You know, the spinning black hole and electric currents and magnetic fields and electric fields. Now let's get to the really exciting part. How does all of this explain what we actually see out there in the universe?
That's the best part, right? Connecting these complex models to real-world phenomena. And I think one of the most dramatic examples is those powerful jets we see shooting out from active galaxies. Sometimes spanning thousands of light years.
Remind me how those jets form.
Sure.
It has something to do with particle acceleration.
Right. Remember those charged particles spiraling along the magnetic field lines near the black hole's rotation axis?
Yes, like they're on a cosmic racetrack.
Exactly. And as they spiral, they're also being pushed along by the electric field, which is aligned with the magnetic field lines in that region. And this accelerates them to incredible speeds, sometimes close to the speed of light.
So it's like they're getting a double boost, guided by the magnetic field and propelled forward by the electric field.
Exactly.
But what happens to those super fast particles? Do they just keep zipping around forever?
So some of them might collide with other particles, releasing their energy in a burst of high-energy radiation, like gamma rays. That could explain some of the intense gamma ray bursts we've detected, but other particles might escape the magnetosphere entirely.
And those escaping particles could form the jets.
Precisely. These particles carrying immense energy stream out along the black hole's rotation axis, forming those spectacular jets we observe.
So these tiny particles accelerated to near light speeds
by the black hole's magnetic and electric fields.
Yeah.
Could be the source of some of the most powerful and awe-inspiring phenomena in the universe.
It's amazing.
It's mind-boggling.
It really is.
Yeah.
And it's a testament to how powerful those magnetic and electric fields can be in the extreme environment around a black hole.
Okay, now let's shift gears for a moment.
Okay.
And revisit the idea of accretion.
Okay.
That process of matter falling onto the black hole.
Mm-hmm.
Right, we're talking about those magnetic field lines connecting the disk to the black hole's event horizon.
Yes.
And if I remember correctly, you said that the electric field could actually pull positively charged particles from the disk down toward the black hole.
Exactly. Those field lines act like channels.
Okay.
And the electric field creates a potential difference along those channels.
Huh?
It's like setting up a slope.
Okay.
Positively charged particles naturally want to slide down that slope toward the black hole where the potential is lower.
So it's not just gravity pulling matter into the black hole.
No.
There's also this electric force at play drawing those positively charged particles in.
Precisely. And as those particles flow toward the black hole, they can contribute to the black hole's growth.
Okay.
And potentially to something even more intriguing.
Okay.
Remember how we talked about the possibility of black holes accumulating electric charge?
Yes. That was one of the most surprising ideas we discussed.
Well, this inflow of positively charged particles could be the mechanism by which that happens.
Wow.
It's like the black hole is a giant battery.
Yeah.
Slowly but surely accumulating a positive charge over time.
So the black hole isn't just a cosmic vacuum cleaner sucking in matter.
Right.
It's also a cosmic power source building up an electric charge.
That's a great way to think about it.
What are the implications of that?
That's one of the big questions researchers are still exploring.
Okay.
But it's possible that for supermassive black holes, the accumulated charge could become significant enough to influence the entire structure and dynamics of the magnetosphere.
So the black hole's own electric charge could reshape the very fields that are responsible for accelerating particles and creating those powerful jets.
It's a feedback loop.
It's a feedback loop.
Exactly. And it's a reminder that these systems are incredibly dynamic and complex.
Right.
The black hole, the disk, the magnetic and electric fields, the particles, they're all interacting and influencing each other in fascinating ways.
It makes you wonder what other surprises are hidden within these systems.
I mean, no, right?
Just waiting to be discovered.
Absolutely. And that brings us back to that intriguing black hole Meissner effect.
Okay.
We've talked about how it's similar to the Meissner effect seen in superconductors, where magnetic fields are expelled.
Right. It's like the black hole is a perfect magnetic shield pushing away any magnetic field that tries to penetrate it.
Exactly. And that connection to superconductivity is what makes the black hole Meissner effect so fascinating.
Okay.
It suggests a deeper link between general relativity electromagnetism and even condensed matter physics.
Wow.
Areas we typically think of as quite separate.
So studying black holes and their magnetospheres could give us insights into superconductivity and other phenomena that seem completely unrelated.
It's definitely a possibility, and it highlights the fact that black holes are far from simple empty voids in space. They're complex objects with powerful magnetic and electric fields that can influence the surrounding environment in unexpected ways.
Well, this has been an incredible journey.
It has.
We've explored this detailed model of a black hole magnetosphere, learned how it can explain those awe-inspiring jets we see in active galaxies.
Right.
And even consider the possibility of black holes accumulating electric charge.
It's amazing, isn't it?
And hopefully you, our listener, are walking away with a sense of wonder. And a deeper appreciation for the complexity and beauty of these systems.
I hope so.
Black hole magnetospheres are much more than just theoretical curiosities. They're dynamic powerhouses that play a fundamental role in shaping the universe as we know it. They drive some of the most powerful events in the cosmos, influence the flow of matter around black holes, and could even hold the key to unlocking new insights into fundamental physics.
That's right. The universe is full of mysteries. And black hole magnetospheres are a perfect example. It's a reminder that even in the darkest corners of the cosmos where gravity reigns supreme, there's still so much to learn and discover.
Thank you for joining us on this deep dive.
Thanks for having me.
Until next time, keep exploring.